sum of all real forces acting on an object. Okay. So this, as I said before, we never really had to establish a coordinate system convention for everything I talked about before. All I said was that the coordinate system existed on the surface of the Earth. So this is the coordinate system convention. It exists at a colatitude that you assign. The convention is that the j hat unit vector points towards the North Pole. K hat is normal to the surface of the Earth, and I hat exists to make this a right-handed graph. Okay? What that makes, omega is an arbitrary combination of j hat and k hat. Okay? And this is it, just dependent on the colatitude. Okay? So, the Coriolis force. This is one of the two forces that arise due to the rotation of the Earth, or technically any arbitrary rotating coordinate system. Okay, it's given by this equation. This is responsible for deviations of objects along their true trajectories. Mostly projectiles, but airplanes covering like transcontinental distances or international distances have to take into account the Coriolis force. But projectiles, most people know, or I don't know if most people know, but I see a lot of people know that snipers, for example, who are trying to shoot up to a mile, their calculations have to take into consideration the Coriolis force. Because if the object is moving in a direction, let's say towards the North Pole, going up and coming down, its velocity is in the JK plane. Okay? When you take omega, which is also in the JK plane, and cross it with the velocity, you get a force that's in the I direction, either positive or negative. It doesn't really matter. Okay, but the point is that if it's going in the JK plane, it's going to deflect a little bit away from the JK plane that it's in. Okay? So that's something that snipers have to take into account. That's a real effect of a so-called fictitious force. Okay? Now, the centrifugal force. Okay, this is the most notorious fictitious force. This is the one that everyone says, oh no, it's not actually there. It's fake. It's just an effect that the normal force has. When you're inside of, they used to have this ride at the fair. They got rid of it because it had killed a couple people. It's like the Ficticious thing or whatever. There's a big one that would rotate, and you'll be able to crawl up the wall. You just stick to the wall. It didn't matter if your feet were on the ground. And people would say, oh, that's the centrifugal force that's pushing you against the wall. And everyone says, no, it's not the centrifugal force. What it is the normal force pushing you into a rotational motion. Because you want to continue going to the side, but then the wall pushes you into a rotation. So it forces you. That normal force forces you into rotation. So it's not the centrifugal force that holds you against the wall, it's the normal force. Okay? That does not mean that the normal force doesn't exist. That is a true explanation for what happens in that scenario, but the centrifugal force definitely exists. It's just fictitious. In the definition that fictitious forces only exist in non-linear force. No. The normal force is a contact force between an object and a surface. Like if I were to put my soda bottle on this table, it's at rest. It doesn't go through the table. The table resists its wanting to push through it by adding an adaptive force.
So the normal force is activated because of the
No. The normal force was an explanation in a non-inertial reference for something that looks like a Coriolis force. The normal force and the Coriolis force are different. That scenario that I explained with the person in the Ficticious or whatever it was called, that is the normal force acting. That is not the centrifugal force. But a lot of people think it is. And so professors and even some scientists will use that example to refute the distinction between Oh no, I meant teachers. Sorry, I meant teachers, not professors, like high school teachers. They'll use that example, saying, "Oh no, that's not the centrifugal force. That's the normal force," to refute the existence of the centrifugal force. It exists. It gets a bad rap for being fictitious force. Yeah.
So is there an example of something where the centrifugal force makes an effect, like with a sniper bullet?
Not in that case, but I'm going to talk about how you see the centrifugal force in a few minutes. Okay, so you consider an object falling to Earth, right? Its position you can just consider only in the K direction. Since it's normal to the sphere, it's just like our hat. It's the same in all directions. It doesn't matter where you are. Your position can always be described as being solely in the K direction. Okay, when you fall, what happens is your position, which is only in the K direction, gets crossed by omega, okay? So that resulting vector is going to be perpendicular to both. When you cross it by omega again, it has to be perpendicular to this vector and perpendicular to r. I mean to omega, which means it has to be parallel to r. So if this was I and this was j, this resultant would be k. So if this was k, k and j would be I, right? So it has to be in the direction of r. Since r is in the direction of k, it turns out the centrifugal force for a falling object points down. Okay? This leads to what's so-called apparent gravity, which I'm going to talk about next. Okay? Apparent gravitational acceleration is the effect that the centrifugal force has on gravity. Okay?
Just a second.
Yes.
Is omega and are omega and tau perpendicular?
They don't have to be, right? Like if you're... Is there a case where it wouldn't? Okay. So, anyway, if it is parallel to r. Oh, well, actually, hold on. No, near the, when theta is 90, I don't think it is, actually. I think they're at the pole, at the equator, and then at the North Pole.
A few times.
Yeah.
Then you get one point perpendicular.
Yeah.
If you take the point there, it's still not the same direction as us.
Okay. I wasn't expecting it to be perfect. I do know, though, that there is at least a component of the centrifugal force that does affect gravity. In the ideal case where it is parallel to r, okay, what you get is you get an additional term that is parallel to g, okay, because g points down, okay, and as I said, until Dr. Rotov pointed out, that's not necessarily always true. In a lot of instances, the centrifugal force points in the same direction as a falling object, okay? So if you drop an object, right, let's say from a building or something, or very, very close to the ground, like 10 feet, 5 feet, you don't notice the Coriolis force. The Coriolis force only exists along a large distance. Even dropping it from the Green Library, it would only deflect a minuscule amount. So you can ignore the Coriolis term in this. And then the acceleration looks like just the gravitational acceleration plus the acceleration due to the centrifugal force. Okay? This is called apparent gravitational acceleration. Okay? And this is dependent upon the colatitude that you are, because omega varies based on the colatitude. Omega varies always for a falling object. It's always going to be in the negative k direction. I mean, or the positive k direction. All right. So the last effect that I'm going to talk about, as far as these non-inertial forces go, is the Coriolis force for hurricanes. Okay. So if you consider just an arbitrary velocity in the ij plane, right? Remember, k points upwards off the surface, so the ij plane is the horizontal plane on the Earth's surface. If you consider just an arbitrary velocity, and you calculate the Coriolis force, what you get is a term that looks like this. Okay, it's a cross product. Once again, I didn't have enough space to actually put the cross product, but it's this. So if you consider in the northern hemisphere, where cosine of theta is greater than 0, okay, because it's the polar angle. When you're above the equator, it's great, it's positive. When you're below the equator, it's negative. Particles traveling north, it'll experience an eastern force. Okay? If a particle moves south, it's going to experience the opposing direction of the same magnitude. It will do the same magnitude of force in the western direction. This is what produces that classic clockwise motion of hurricanes in the northern hemisphere. Okay? If you notice, in this term, in the southern hemisphere, cosine theta is going to be negative. Okay? The unit vectors will point in opposite directions, so you'll get the counterclockwise rotation of hurricanes in the southern hemisphere, or tropical cyclones, or whatever they're called in the southern hemisphere. Okay? This, as I said before, is also responsible for deflections of projectiles from their true trajectories, which would be trajectories in a non-inertial vector stream. It's supposed to be the parentheses over here. Okay? And since omega is small, right, the rotation of the Earth is fairly slow. the force is only apparent over large distances, or actually large amounts of time. Right? It has to be going for a while before you notice the effect. That's why hurricanes is very, very apparent. Hurricanes are huge, spanning sometimes hundreds of miles in diameter. So it's apparent in something like that, but it wouldn't necessarily be apparent if you were to throw a football across this room. It's not like it would go and then deviate, so if I threw it to him, it would reach you. Alright, so that's about it. Like I said, non-inertial reference frames or accelerating reference frames, they produce forces associated solely to the acceleration. And these forces are commonly referred to as fictitious or pseudo forces. They do not appear in inertial reference frames. And they are not due to the interaction between particles, only to the acceleration. And they, as I said, they're very real in the sense that they do affect everyday life, and they do affect the physics that we experience. All right. Any questions?
So, I don't know if I missed it, but was there an example on the centrifugal force happening or something?
Yeah, affecting gravity, so apparent gravitational acceleration. If you consider an object close to the surface of the Earth, then the Coriolis force can be ignored, because as I said, it needs to act over a large distance. And then there are instances, though I need to work out the math again, because Dr. Yota pointed out that it might not necessarily be true. The only fictitious force that would appear on an object falling to Earth, close to Earth, would be the centrifugal force, and that affects the total acceleration. So the total acceleration would be just the gravitational acceleration plus the centrifugal, the acceleration term associated with the centrifugal force. So that would be called G star.
So if I had the Earth and I had an object falling towards Earth and the Earth is spinning, the centrifugal force would then move it?
No.
That would be the other one?
No, centrifugal force would pull it to the Earth faster. There's actually an explanation for the Coriolis force using angular momentum conservation about something like that. But that's for the Coriolis force, not for the centrifugal force. Though that explanation doesn't necessarily work all the time. It only works for a falling object. So it's not a very accurate explanation. Yeah.
Are there any fictitious forces that, other than these examples, that might appear in Einstein's equations?
I knew I'd get a ridiculous question. Not ridiculous, but ridiculously difficult. The thing about Einstein's equations are that I don't think that they're done for they're done. Oh shoot, they are done for non-inertial reference frames, aren't they? Yeah, I mean, I don't know how to answer that question. I've never done anything like that before.
But do you know other examples?
Well, I mean, any accelerating reference frame would produce a non-inertial force term that would change your measurements. So if you were to, instead of trying to measure some value in an inertial reference frame, if you had that reference frame still accelerating forward, like linearly accelerating, it would change the values of some things we were trying to measure, like momentum and stuff. You could have one particle accelerating and its momentum would be changing, even though it's not experiencing an external force. Any reference frame that's